Welcome back. This is now part 2 of the second video series on section 7.2 of the dot product. We continue where we left off, now completing questions 6 through 8. Let's begin. So question 6 asks us to calculate the dot product of the unit vectors I and j, first using geometric vectors and then using Cartesian vectors. Alrighty, so this was I dot j. Let's first do it using the geometric dot product. So we have mod I, mod j, cosine of the angle between them, and we get 1 cosine of 90 degrees, which is just 0. And then for the geometric, for the Cartesian dot product, sorry, I dot j, we get 1 times 0 plus 0 times 1. Because remember that I is equal to the vector 1, 0, while j is the vector 0, 1. Okay? And as we expect, we also get 0 here. So this is the geometric. I guess I'll write it off to the side. In this case, we're doing the geometric. And in this case, we're doing the Cartesian. Good. And then asks us to explain our results. Well, we know that they should be equal. Both the dot products should be equal. That's one thing we know. And also, I guess a more in-depth look into these guys and a bit more beyond the scope of this class, I guess. But I and j, you can say, constitute a orthonormal basis. And so this word orthonormal, it's not that complicated. It has the prefix ortho, which means orthogonal. So I and j are orthogonal, as our dot product told us. And normal just means they're of unit length, each of the vectors I and j. So I and j together as a set form a orthonormal basis. That's just a fancy way of saying that any vector in the Cartesian plane can be made from I and j, which themselves are orthonormal. That's what basis means. Okay, good. Let's move on. Question 7. So I'm not going to do all of these. So let u be that vector, v be negative 6, 1, and w 4, 7. Evaluate each of the following. If possible, if it is not possible, explain why not. So I want to quickly go through and explain which ones you can't evaluate. So one that jumps straight up at me is this one, g. This is, you can't evaluate this. So the reason being is this. Let's say you do u dot v first. That results in a scalar. But then you have a scalar dot a vector, which is not allowed. Right? So that can't happen because, again, the dot product is an operation that requires two vectors. Not a scalar and a vector, not a vector and a scalar, two vectors. So that's wrong. Okay. The other one, I guess, that jumps out at me would be this one right here. D. So why is D not allowed? Well, D would be like, right here, we get a scalar after applying this dot product. So we would get u plus some scalar. Now, vector addition is an operation that needs two vectors. So you can't just have two these quantities are not the same type, right? You have a vector plus a scalar, so that's also not allowed. Is that all of them? Just making sure I didn't miss any. Yep, that seems about it. Okay, so I guess we can move on now to the actual exercises themselves. So I'm not going to do all of them. Let's do, I like F. Let's do F. So we have 5u dot 2v minus w. Okay, so we have 5. The vector u is 3, negative 5 dot 2 times the vector v, negative 6, 1, minus w, 4, 7. Okay, so let's do the scalar multiplication first. We have, that would be 15, negative 25. We have dot. We can do the scalar multiplication on the inside as well. That would be negative 12, 2 minus 4, 7. So then we can leave this vector on the outside here and then complete this vector subtraction inside the brackets. Minus 12, minus 4, minus 16, and then 2 minus 7, minus 5. But yeah, it's just a component-wise subtraction. And then what do we get? We get 15 times negative 16 plus negative 25 times negative 5. So 15 times negative 16 plus negative 25 times negative 5. We get negative 115. Okay, that's F done. Let's do H as well. Let's do H and J. So we have U plus 2V dot 3W minus U. So then U is the vector 3, negative 5 plus 2, negative 6, 1. Close the parentheses, dot 3, and then W is the vector 4, 7 minus 3, negative 5, the vector 3, negative 5. Okay. So we get 3, negative 5 plus negative 12 plus negative 12, 2. That's just doing the scalar multiplication, dot 12, 21 minus 3, negative 5. Okay, now we can complete all the operations of the parentheses and then dot them at the end. Again, for all these questions, we're just following order of operations the way we see them. So, in each of the parentheses, we get 3 plus negative, so 3 plus negative 12, that's negative 9. Then negative 5 plus 2, negative 3. Dot 12 minus 3, that's 9. and then 21 minus -5. 26. Now just doing the dot product, -9 times 9 plus -3 times 26. And the final answer we get is -159. Okay. And let's close the show out with J as well. V dot V plus W dot W. So even actually, the reason I like J is because before we even start inputting our stuff, we can actually just simplify this using one of the vector identities, or the vector one of the dot product properties. Sorry. So V dot V is just V squared, and this is plus W squared, right? That's by 4. If we go back, 4 right here. You can call this the modulus property if you want a name for it. Okay, so you could always do the dot product as well, but I like this way better because I see a property, I'm going to use it, I think. So you should think as mathematicians. Okay, so then we just find the modulus of V and the modulus of W, and we square them. So for V, that would be -6 squared plus 1 squared. So we would get square root 37. But then that's squared plus W, which is 4 squared plus 7 squared, square root 65. But again, that's also squared. So then you just get the square roots will cancel and you get 37 plus 65, which is 102. Good. And yeah, you could have done it the alternative way, we dot them first as well. Both are fine. Okay. I just want to make a clear distinction of when I'm using the properties. I guess I'll put them in red so you know that I'm using one of the properties. And I didn't mention it here. All right. I guess technically speaking here as well. Okay, now moving on to question 8. Always consistently run out of room, it seems like. I'll do it off here to the side. So which of the following is a right angle triangle? Identify the right angle in that triangle. Triangle ABC, and triangle STU. So I'm just going to draw 2 Cartesian grids just to get a rough idea of where they are, of where these points lie. Again, this is a very rough, not to sketch drawing, but it's always good to do so. So 3, 1, let's say that's like somewhere here-ish, A, B, negative 2, 3. Somewhere around here. And then C, 5, 6. Okay. And then STU. So we got 4, 6. It's somewhere here, let's say. T, negative 3, 7. And U, negative 5, negative 4. Let's say it's somewhere here-ish. Okay. So the way I would do this to identify the right angle in that triangle. So I would first get some side lengths of each triangle down. So let's do that. So for A, let's define side lengths AB, BC, and CA. So we have AB, AB would be, you have negative 2 minus 3, and then negative 2 minus 3, and then 3 minus 1. Do that in a bit. BC, we have 5 minus negative 2, and then 6 minus 3. And then we have side length CA. And side length CA would be CA. So it would be 3 minus 5, 1 minus 6. 3 minus 5, 1 minus 6. Yep. Now let's get the vectors as position vectors. Minus 2, minus 3, minus 5, 3 minus 1, 2. 5 minus negative 2. Oh, sorry. Yeah, 5 minus negative 2. 7. And 6 minus 3. 3. 3 minus 5 is negative 2. 1 minus 6 is negative 5. All right, and then I'm just going to, a good way to determine if there's a, if one of these angles is a right angle triangle, is just dot every pair of one of these side lengths I see and see if any of them gives me 0. Whichever pair of side lengths gives me 0, that's where I know the right angle will be. So there's a lot of pairs to go through. I'm not going to go through the whole, I'm not going to show the calculation explicitly here because I'm running out of room. So AB dot BC, we'll do that one. See what we get. We'll do AB dot CA, see what we get. BC dot CA. And remember, we don't have to do CA.BC or CA.AB or BC.AB because the dot product is commutative. So once we do it one way, we already know the other way is going to give us the same answer. Okay, so let's go through these. So we have negative 5 times 7 plus 2 times 3, negative 29. So that one's definitely not it. Just make sure to get it again. Yep. Negative 5 times negative 2 plus 2 times negative 5. And there's our match, ab.ca. So let's just check the other one, I guess, for good old sake. 7 times -2 plus 3 times -5, -29. So there's our pair. Meaning ab.ca. So the right angle is somewhere here. Okay. That's good. Now let's do it the same thing, same ordeal for the STU triangle. So let's find the viable side lengths. So ST, we have -3 minus 4 and 7 minus 6. Okay. And then we have TU. Let's do TU. TU would be -5 minus -3. And then -4 minus 7. So STTU, let's do US as well. The good old US of A. US, so we have 4 minus -5. Four minus -5 and 6 minus -4. Let's just see if that one makes sense. Oh, I have a unnecessary comma here. That shouldn't be there. We have 4 minus -5, yep, and 6 minus -4. Yep, good. Okay. Now let's calculate all these position vector side lengths. -3 minus 4 minus 7. 7 minus 6 is 1. -5 minus -3. It's -2. And -4 minus 7. -11. 4 minus -5. It's 9. 6 minus -4 is 10. All right. And let's compute each pair of side length dot products. ST dot TU. Make sure to add the vector symbols. ST dot US. And then TU dot US. All right, let's compute the dot products. So we have -7 times -2 plus 1 times -11 is 3. ST, so -7 times -2 plus 3. ST.US, so -7 times 9 plus 1 times 10, -53. Okay, and then TU.US, -2 times 9 plus -11 times 10, -128. Okay, so since none of these dot products actually yielded 0, that means there is no right angle present within the triangle. And if there's no right angle present within the triangle, we know the triangle cannot possibly be a right angle triangle. So triangle STU is automatically ruled out for not being a right angle triangle. But triangle ABC is. Okay, good. Now, part B. So what is part B asking us to do? Part B asks us to describe another method for solving the problem in part A. Okay, so one method you could do is, now that you have using the side lengths of each triangle, compute all of their respective magnitudes. Then check if the Pythagorean theorem holds for the specific triangle. So once you find the magnitudes of all the triangles, whichever one is the largest one will be your hypotenuse, and then you check to see if the other two squared will equal the hypotenuse squared, because that only ever holds for right angle triangles. If it doesn't hold, that means your triangle's not a right angle triangle, so there will be no right angle to find anyway. Good. That answers 6, 7, and 8. Quite long, sorry. We'll move on to the remaining problems in part 3. Thanks, guys.